Hello and welcome again. In the previous video, we started discussing about the key schedule, and we saw that the key schedule has rounds, and every round looks almost exactly like this one. So this structure here is exactly the same. So there's a lot of XOR that is going on in here. And remember the last video we explained how to get from this stage to this stage doing this sort operations. Now, the only thing we didn't discuss in that video was the inner structure of this G function, which remember takes an input, which is a 32-bit block, and it's going to output a 32-bit block. So now in this video, we'll discuss about this function, what is the structure and what the function is doing to transform this 32 bits in another 32 bits. So let's look at that here. So this diagram that you can see there is the structure of the G function, and it depends on the round. So the round, whatever the round is, if it is round 1, 2, 3, up to 10, because remember we are discussing the rounds for the 128-bit key. There are more rounds if you increase the key size. Now, if you are in round I, so what you do is, okay, the input is always 32 bits. Here, that's what this arrow here indicates with this diagonal thing here, 32-bit input. Now, this is the 32-bit input, and what you do is you're going to imagine that you're going to divide that in 2 bytes. That's what the V0, V1, V2, and V3 are. So those are the bytes. So we have 4 bytes of this 32-bit block that is here. So that's why we put the 8 there. I hope that's not too small for you to see. So those are the bytes there. This transformation that goes from here to here, basically what we are doing is we are doing a shift left of one position to the left. So basically what this stage here is coming from here. Imagine that this V0 that is here, let me use some color, this V0 will go to the front here. That's a shift left of one position. So then you end up with V1, V2, V3, and V0, which is that one right here. So again, this one over here, this transformation that goes from here to here is just a shift left of one position. And then here we are doing this with bytes, not with bits. So we're going to move the whole byte here to the end of this block. So we're going to end up with V1, V2, V3, and V0. So it's a rotation left, basically. That's what we are doing here. Now, so once we get this new 32-bit, which is only a rotation left from the input, which is this one right here. Now, every byte is going to be transformed using the X box. And this is the X box we use in the advanced encryption standard. Remember when we did the byte substitution, which is that very big table, and then you have to transform your bytes into hexadecimal of 2 components. Then you apply this X box, and then you end up with whatever is the output here. Now, if you don't remember that, I'll suggest that you go back to that video and watch the byte substitution transformation. That's what the X box is. So you will find out how to do it. There was a homework for that, and there was also videos for that. So go and watch that, because that is going to be important here in this G function. So the G function, what it's going to do is going to apply the X box to each individual byte here, V1, V2, V3, and V0. And so we're going to apply it there like this, the X box. So this is the meaning of this. This is the X box we saw a while ago. So again, go ahead and watch the video to see how that is done. That's transformation from one byte into another byte. Now, there's another thing here, which is, well, a couple of things. One is the sort that is here, and this RCI. Now, this RCI is what makes this G function depend on the round. So if I'm in the first round, I'm going to apply RC1, and if I'm in the second round, I'm going to apply RC2, and so on and so forth. So this RC1 doesn't really have any input. It's just it's going to be just a byte, so it's a bit. And I'm going to take that byte, and I'm going to sort that with whatever the output was from the S function from V1. So take this V1, transform with the S function, and then you get another byte here. You're going to sort that with RCI. and then you're gonna get, of course, 1 byte here. So once this transformation is done, I'm gonna get in this line here, I'm gonna get a byte. This V2, you just apply S, you don't S box, you don't have to apply RCI here. And then you put them all together. And so when you put them all together, you get your 32-bit block. Okay, so everything that is here, we know how to do it. Rotation left or shift left of 1 byte, which is here. The X boxes, which is correspond to that table with the byte transformation. We know how to do that. We know how to do sort, and then the only thing that is a little bit mysterious here is this one, but it's actually very easy. So this is just a byte. It depends on the round. So let me look at that. What is the byte here? The RCI for any I from any round from 1 through 10, if we're talking about the 128 key size, is gonna be x to the I minus 1 in the Galois field. So what I mean is the power of this number, subtract 1, represent this power that is right here in this Galois field, and then put it back into a byte. So let's see a little bit of examples here. So what is RC? I have a list here. So what is RC1? So RC1 will be x to the 1 minus 1, because it's always x to a power that is less than this index that is here. So 1 minus 1. So that will be x to the 0. X to the 0 is 1. So, and 1 represented as a byte. Remember that it's just if you organize your byte coming from left to right, the highest power here, x to the 7, x to the 6, and so on, then 1 will be just this byte right here. Now, similar with RC2, RC2 will be x to the 2 minus 1, because it's always 1 less than this index that we have over here. So that will be just x, and that x is represented by this byte, in a similar way with RC3. Now, the only thing that you have to do here is when you get to higher powers, because remember, all of this has to live in the Galois field, then when you get to this RC9 or RC8 here, then you will have to do the transformation. Actually, RC8 is okay. The one that you actually have to do is RC9 and RC10, because what is RC9? Is x to the 9 minus 1. It's always 1 less, which is x to the 8. Now, x to the 8 is not an element of the Galois group, so you have to reduce it. How do you reduce it? The same way we reduce with the polynomial. Remember that important polynomial that is x to the 8 plus x to the 4 plus x cubed plus x plus 1. That was the important polynomial. Now, because I have to transform x to the 8, one way to do it, which is very easy, is just replace x to the 8 by the equivalent powers, which are these ones over here. So x to the 8 will be x to the 4 plus x cubed plus x plus 1. And now I can represent this polynomial, which is in the Galois field. I can represent it like this. And you can double check that this is the byte representation, because this is x to the 7, x to the 6, x to the 5th, and x to the 4. And then you will see that that is exactly this byte that you see right here. So it'll be this representation. Now, RC10 will be the same. You have to know how to transform it. So RC10 will be x to the 10 minus 1, which will be x to the 9. Now, remember, you have to reduce this x to the 9th with the polynomial p, and remember what you do is you take this x to the 9 and express it in powers of 8. In this case, this x to the 9th will be x to the 8 times x. And so if you do that transformation using this substitution that I'm marking down here with the red arrow, then you're gonna end up with this byte, and you can go ahead and double check that this is actually the correct byte that we get from x to the 9. So now we explained all the RCs that are here. So let me go scroll up again. So we know what this is. So this guy here is a byte that depends on the round. So if I'm in the first round, then we're gonna use RC1, and then we're gonna sort that with whatever the output of the S box is coming from the V1. So, and then that would be this guy here, this output will be the first byte of my final 32-bit block. All right, so that's basically what the G function is doing. So what I want to do now is I want to give you an example. I'm not going to be able to give you exactly all the details, because we have to go through the X box, and the X box is a kind of like a little bit of a long process to transform all the bytes. So, but this is gonna give you an idea what the transformation is. So let's transform. Let me put here an M. Transform the following 32-bit block. So I'm assuming that this 32-bit block that I have over here is the input of my G function. So I'm gonna take this as an input of my G function. So this is a 32-bit block that I have over here. Now the first thing you're gonna do is you're gonna imagine that you're gonna divide it into bytes. So we're gonna divide it into bytes, and of course we're gonna transform that with the G function. And they always have to tell you which one is the round, because remember the G function depends on whatever the round is. So it's going to act in a different way depending on the round. So in this case, let's assume that we're going to do this for the last round with the 10th round. So this 32-bit block that I have here is the input of the G function in the 10th round of the key schedule. All right, so the first thing I'm going to do is, of course, you're going to take that 32-bit that I have over here, and we're going to divide the block, the 32-bit block, into bytes. And we're going to call it V0, V1, V2, and V3. And that's exactly what I have over here. I'm marking that down with yellow. So this V0 is going to be the first 8 bits or the first byte that I have here. And if you notice this first 8 bits are exactly the same, the first 8 bits that you have here. And then V1 will be the next one. V2 will be the third one. And V3 will be the last one, or the fourth one. So I took the 32-bit divided into bytes. All right. After that, we're going to shift left the bytes 1 position, which is exactly what the G function does first. The G function is going to shift left the bytes 1 position. So this V0 will now go to the end, and then this V1, V2, and V3 will move here to these positions. So if we do that, so what you end up doing is you have V1 first, V2 second, V3 third, and then the last one will be V0. That's the shift left of the bytes. And then we ended up with this here. Now, next thing we do is, remember, we're going to take every single of these bytes that are here, and we're going to apply the S function to every single byte that we see over there. Now, and I want to be able to give you exactly all the details there, because otherwise this video will be extremely long. So what I'm going to do here is I'm just going to give you the output of the S box here for each individual byte that I have over here. So that's exactly what I'm going to show you now. So what I'm going to show you is I have V1 here, which means this whole byte. V2 will mean this whole byte. V3 is this byte, and V0 will be this byte. And I'm going to transform every single byte that I have there with the X boxes. So I have V1. If I have transformed that with the X box, it's going to give me this byte. Now, if you don't believe me that, you can go ahead and check and double check that this is actually the byte that comes out of the X box when I apply that V1 to V1 here. And then to the V2, apply the X box and you get this byte. Same thing, V3, I apply the X box and you get this byte. And finally, the V0, I apply the X box and you get this byte. Now, the reason I'm marking this down here, you see these numbers 2, 3, and 4, is because my final 32-bit will have this 2 here is the second byte in my final answer. This third here is going to be my third byte in my final answer. And this 4-bit here is the last byte in my final answer. The reason this guy, remember, is not the first byte is because I have to sort this V1 with RC10. And remember, let me scroll all the way back here because let's just emphasize that this one, the V1 that is here, the output of that is the Xbox. I have to sort it with the RC10 in this case because we are doing the 10th round. So let me scroll all the way down again here to go back to the computation I was doing. So let's see here. All right, so that is why I don't mark this as 1, this output here, because I still have to take this byte and sort that with RC10. So that's what I'm going to do here. So what I have here is the output in this part. This is the output of the S box for V1. And then you look at this one here, it's exactly the same as the one that I have over here. I have to sort, bitwise sort with RC10. Now I wrote it down over here. So the RC10 is this byte, and you can go ahead and double check. I had it up there. So I'm gonna bitwise sort of this output of the X box for V1. I'm gonna sort it with this one. And if you go ahead and do that, then you're gonna get this byte here, and you can see exactly why this is here, the answer for that one. And I'm marking that as a 1. So that's what gonna be my first byte of my answer. This is my first byte. This guy over here would be my second byte, third byte, and the fourth byte. So the output then of the G function will be my first byte, my second byte, my third byte, and my fourth byte, which are marked down with yellow. And then we ended up with this 32-bit. So I put all of them together. The first byte is right here. The second byte will be here, and so on and so forth. So this is gonna be the output. This one right here is the output of the G function during the 10th round using the 32-bit that we saw at the beginning. So that's exactly what the G function does. So with this, we actually completely saw what the rounds of the key schedule is going to do. Now remember that the G function depends on the round. So depending on the round, you're going to use a different RC. And the RC is just a byte that you have to sort with the first byte after you do the transformation with the X boxes. So this completely determines already what the key schedule does. So basically, we are done with the key schedule. So this is it for the key schedule, only for the 128-bit length. Now, if the key is a little bit larger, then the rounds are going to increase. The structure of the rounds is going to be a little bit different, but they're going to be very similar to the structure that we have here for the 128-bit length of the key. So what I'm going to do is I'm going to stop the video now. And in the next video, we're going to discuss a little bit about the other key schedule for the other key sizes. So I'll see you in the next video.